So for the hands-on training, so first you need to open your software. You can see this is my C drive. This is my device studio folder. This is my bin folder. And here you can see this is my device studio application file. So this file you need to open. So once you open the device studio, here you can create a new project. Then you can enter the project name. You can see this is my project name. Then you can choose the location where you want to save this project. So any location you can select the save option. So you can see this is my device studio. That is a graphical user interface of the NanoDCAL and Rescue software. And this interface will help you to model the structure. You can create any structure, like you can create a molecule, you can create any device structure, you can also create the surface structure, symmetry structure, graphene nanoribbon, nanotube, grain boundary, nanotube structure, nanowire. These are the graphene-like structure. These are the zinc blend-like structure, icosahedron, ectohedron. So this device studio will help you to build your structure. And once you create the structure, then you can select the simulator. And in the simulator, you can see we have multiple simulator. Like we have the NanoDCAL, that is basically for the atomistic quantum transport simulator based on the density function theory and non-equilibrium green function theory, so that you can simulate any material and any device structure. Also, we have this nano scheme that is basically for the tight bonding model of nanostructure. This is the rescue that is dedicated for the material simulation. So any material based on the density function theory and density function perturbation theory, you can simulate. And you can see this is the advanced version of this rescue. So this rescue is written in Python and Fortran. So I hope everyone has been open their software. So first, you can simulate some material based on the NanoDCAL software, from the NanoDCAL software, and after the material, you can simulate the device from this NanoDCAL software. So first, you can import some simple material, simple structure, so that you can study. So during this session, you can follow the same procedure that I will show you. And after this session, you can create your own structure. So you can see this is the file option. And you can import some material from our database. So if you want to import any material, you can select the file option, select the import, then select this import local. Now this is the import local option. And you can import some silicon semiconductor. And based on the density function theory, you can analyze their various properties. So that I will show you during the demonstration. So first you can import some material. So this is our 3D material, semiconductor, and you can search silicon semiconductor. So for importing this silicon, you can select import local, then go to this directory. You can see this is my C drive, this is my device studio, this is the material folder, 3D material, semiconductor, and here you can see this is the silicon semiconductor. So you can take this silicon, select this open. You can see this is the simple silicon structure where we have two atoms. So two atom we have. You can see this is the vector value, vector A, vector V, vector C, and this is the total number of atom. You can see this is the total area of this lattice. So I hope everyone has been imported this silicon structure. So after importing this silicon semiconductor, we need to simulate this structure. So for simulating any material, any device, we need to select the simulator. You can select this NanoDCAL, then select this SCF calculation. So this is basically self-consistent field calculation, so that you can define your density function theory parameter like electron temperature, cutoff energy, exchange correlation function like LDA, GGA, K-point sampling, iteration control like density matrix, Hamiltonian matrix. Also, you can define some Spintronics application. So you can select this self-consistent field calculation. And here you can see these are the basic parameters that we need to enter. So you can see this software has taken this default parameter. If you want to change any parameter as per your research, you can change. So you can define your own parameter as per your need. I am taking the default parameter that software has already taken. So these are the basic setting: electron temperature, cutoff energy, exchange correlation function, K-point sampling. These are the iteration control parameter. This is the basis set, and this is the spin type. So first you can simulate some material. After the material, I will also show you how to simulate any device. So once you define all the parameter, you can select this generate file so that their scf.input file will be generated. So I hope everyone has been generated this scf.input file. Now we can move on the simulation. We need to run this scf.input file so that it will generate NanoDCAL object.mat file. So we need to select this input file.
Sir, sorry to interrupt, but sir, Here in project, I'm seeing that NanoDCAL crystal, but SCF input file is in my folder. It's not showing in this project section. What should I do?
So where it has shown this
Uh,
SF.in.
Sir, this PC in folder, like it's not showing in this interface.
So you can click on this arrow, then you will find this input file.
No, sir, it's not showing.
Can you send me the screenshot?
Uh, Sir, it's on another screen. So, sir, wait, I'll send.
Okay, very nice. So once you click on this generate file, then you will find this silicon folder. You can click on this arrow. Then you will find this NanoDCAL crystal folder. Again, you can click on this arrow. Then you will find the SCF.input file. So now we need to run this similar input file. Can you click on this arrow?
Sir, I'm clicking, but it's not showing. So when I'm doing right click on this and open containing folder, then it is showing that HCF.input file, but here it's not showing.
Okay. Okay, ma'am. No, so after this session, I will take the access of your system and then I will check that problem.
Okay, fine, sir.
So you can see this is my scf.input file and we need to run this input file. So if you want to run any input file, first you need to select that file, right click, select this run option. And again, you need to click on this run option to run this job. Also, you can run the job on parallel core, suppose 5 core, 10 core, 15 core. So there is no limitation of core. You can define up to 128 core. But we have given you the evaluation license. So you can see default 1 core has been selected. But once the user will purchase this software, then we will provide you the cluster license so that you can run the job on parallel core. So now we need to select this run option to run this job. And here you can see our scf.input file is in the running condition. So after running this scf.input file, in the meantime, you can go for the analysis. So for analysis this properties, we need to select the simulator. Then we need to select the NanoDCAL. And here you can see this is the analysis. So you can select this analysis. And you can see these are the different material property that you can analysis. So for any material, every analysis parameter you can study. So you can select whatever parameter you want to analysis. You can double click, then the parameter will be selected. Also, you need to define the parameter for this density of state. Here you can define some k-point sampling. Like you can see, I would like to take default n1, n2, n3 is equal to 5. So this is my density of state analysis parameter. You can select this band structure. You can see this is our symmetry K point. So this is our midline zone path. And here we have the symmetry K point. And for the total energy calculation, you can see we need to write this command. So we need to write this command for the total energy calculation.
Excuse me, Deepak sir, from where did you get this command that you have copied?
So from this website, document and tutorial, NanoDCAL. This is the
Okay.
input reference, calculator parameter. Here you can see, this is the total energy. You can see, this is the command.
So can you please repeat for last 30 seconds after the band structure you have selected?
Okay. Like you can see, this is my band structure that I have selected. And if you want to calculate the total energy, so this total energy, if you want to calculate, then you need to write this command. So this command you need to write.
Sir, for the time being, send this command on the WhatsApp or in the chat box so we can copy it directly from you.
Yes, ma'am, I am sending this command so that you can
Okay,
copy
thank you, sir.
and you can paste in the input file.
Okay, sir.
You can see this is the command that I would like to share.
So please share on chat box.
Okay. So this is for total energy. And for this Phonon Band structure and ZT, first we need to calculate the Hessian matrix. So we can select this Hessian. Here you can see this is the Hessian matrix parameter. Then you can select this Phonon Band structure. This is the electron density. You can select this parameter, electron density. Again, you can select this potential. You can see effective potential, Hartree potential, exchange correlation potential, and neutral atom. Like if you want to calculate the Coulomb potential, then you need to select this Hartree. So I have selected this density of states, and these are the parameters. This is the band structure, their parameter. This is the Hessian and their parameter. This is the Phonon Band structure, their parameter. This is the electron density. You can see this is the charge density. This is the potential. And in the potential, you can see I have selected this Hartree potential so that we can calculate the Coulomb potential. This is the transmission channel. So you can see this is the transmission channel parameter. And for you HOMO and LUMO, we need to select this Eigen state. So you can see this is the Eigen state parameter. So this parameter is basically for the HOMO and the LUMO analysis. Like if you want to analyze the LUMO or HOMO, so here you need to change the number of band. If you select the 10, then it will generate the input file for the HOMO. And when you select 0 and 1, then it will generate the input file for the LUMO. So HOMO and LUMO value is also possible. So you can see this is the HOMO value that I have entered. So for the HOMO, 1 and 0, and for the LUMO, 0 and 1. So once you define the parameter, you need to select this generate file so that their input file will be generated. So I hope everyone has been selected the parameter and also they have defined the parameter. So once you define all the parameter, you need to click on this generate file so that your input file will be generated. You can see the input file has been generated. And I hope your scf.input file has been completed. You can see it has taken 38 seconds for simulating the scf.input file for this 2 atom. So once the file completed, we need to run all this analysis input file. Like you can see, this is our density of state input file. You can select this band structure input file, Hessian.input file. You need to select this Phonon band structure dot input file. So every analysis parameter you need to run. So you can run all this analysis input file in the queue condition. Here you can see I have run the input file in the queue condition. Like when this file will be completed, then this bandstructure.input file will start automatically. So there is no need to run one by one. You can run simply in the queue condition. So in the queue condition, you can run multiple input file. And once the simulation completed, then it will generate a output file. You can see this density of state is simulating by using the wave function method. So by using this wave function method, it is simulating the density of state for this material. And if you simulate the device density of state, then with the help of green function method, it will simulate. So wave function method will apply for the material and green function will apply for the device. So you can wait till the simulation complete. And once the simulation complete, it will generate a output file. Now you can see our density of state has been completed and the output file has been generated. So once your simulation complete, then you will get the output file. So I hope your density of state and band structure output file has been generated. So it will generate once the input file will be complete. So in my computer, you can see the input file has been completed and their output file has been generated. And to show the graph, yes, sir.
Can we calculate the band structure for a spin up and spin down?
Yes, sir, we can calculate. So that you need to define some Spintronics application that is collinear.
Can you show me one more time?
Like if you want to calculate the Spintronics application, you need to select simulator, NanoDCAL, select the SCF calculation.
Okay. We have to specify in say SCF calculation.
Yes.
Okay. Thank you.
And here you can define collinear spin.
I forgot to assign the spin type.
Okay, sir. No, sir. So once you define here collinear spin, then you will get the output for the any structure like band structure, density of state, their spin up and their spin down result. So after this material simulation, I will show you how to simulate any device structure. You can see density of state has been completed and their output file has been generated. So for showing the graph of any output file, first we need to select that file, right click and select this show view so that you can plot the graph. You can see this is the density of state with respect to energy in the unit of electron volt. And here you can see we have the number of state per electron volt. So this is the energy range. Here you can see we have the density of, we have the Fermi energy. This is the density of state. Similarly, you can analysis all this parameter. Like this is the band structure. You need to select, right click, select this show view. Here you can see this is the band structure of the silicon. So we have the conduction band, we have the valence band, we have the Fermi energy. You can also calculate the band gap, so that you need to import the mat file into MATLAB so that you can get the data like conduction band energy, bottom of the conduction band energy and top of the valence band energy, so that you can calculate the band gap. Similarly, you can see this is the Phonon band structure. So this is the Phonon band structure. This is the high symmetry K point. This is the Phonon energy. So every parameter you can analysis from this show view option. Like you can see, this is the total electron density 3D view. This is the 2D view. And this is the 1D view. You can see this is the Coulomb potential. The potential you can see, I have selected this Hartree potential so that you can calculate the Coulomb potential. You can see this is the Coulomb potential. So from this visualizer, you can visualize either 3D view, 2D view, or 1D view. So this is the transmission channel. You can see this is the number of transmission channel averaged over transverse K space. And also this is the Eigen state. And in this Eigen state, I have selected the HOMO, like the number of band I have selected 1 and 0, so that we can plot the Eigen state for the HOMO. And here you can see this is the 1D view. So I hope you have an idea like how to simulate any material from this NanoDCAL software with the help of density function theory.
Sir, can you calculate the energy? Sure.
1 second, sir. You can see this is my command for plotting the graph. So if you write this command, then it will generate a mat file. But if you write this command, then it will also generate a graph. Mat file, also it will generate the graph. So we need to save this input file. And then we need to run. As you can see, the simulation has been completed. And if we talk about this open containing folder, here you can see this is the total energy mat file. And if we talk about the graph, You can see the graph has been generated. You can see these are the various energy: kinetic energy, VNA energy, VNL energy, V effective energy, band structure energy, real space energy, real space DVDS energy, Harting energy, real space energy. And if we talk about the value, like you can see, you can see this is the total energy value, short range energy, delta local energy, ion energy, real space DVNA energy. So all the energy and their value are mentioned. Talk about this description.
Okay, thank you, sir.
You can see kinetic energy, band structure energy, and also you can see total energy. So you can double click on this mat file, totalenergy.mat. You can type the command data, press the enter, so that you can find the energy and their value. If you want to show the theory, like how they can calculate these properties, you can type delta dot description. So this command you can write so that you can plot the graph. So I hope you have an idea like how to simulate any material from this nanodical with the help of density function theory.
Yes, sir.
So now we can move on the device simulation. So I will take some simple device structure, because once you increase the number of atoms, then your simulation time will increase. So it is better during the session to take less number of atoms. So I would like to create a graphene nanoribbon device structure. So for creating a graphene nanoribbon device, you need to select this build option. Here you can see this is the graphene nanoribbon. So for creating graphene nanoribbon, first you need to select this build option, then select this graphene nanoribbon. You can see this is the graphene nanoribbon builder that will help you to build your nanoribbon structure. First, you need to select the element. For the graphene, we need to select the carbon. If you want to create another nanoribbon, then you can change the element from the side A and side B, so that your desired nanoribbon will be created. You can also change the bond length. If you want to passivate dangling bond with the hydrogen atoms, so passivation you can also include, so that you need to enable this option. You need to define some structure type, the Kroll vector, the n and am value. So any combination you can select. Also you can generate the either armchair structure or zigzag structure. So for the zigzag structure, we need to define the same number of Kroll vector, and for the armchair structure, we can define m is equal to 0. So you can see this is the 2 by 2 zigzag graphene nanoribbon. So this is the zigzag structure. If you want to show armchair, then here you can define 0. Select this preview, and you can see this is the armchair graphene nanoribbon. So any structure as per your need you can create. I would like to create a zigzag. So I need to define n is equal to 2 and m is equal to 2. So you can see this is the 2 by 2 zigzag graphene nanoribbon. So you can define Kroll vector 2 by 2. Select the preview. Select this build option. So I hope everyone has been created this 2 by 2 zigzag graphene nanoribbon. And you can see this nanoribbon is quite thin. So it is better to increase the length so that we can define the left electrode, right electrode, and center region. So if you want to increase the length of this nanoribbon, you need to select this build option. Select this redefine crystal. So if you want to increase the length, first you can select this build option, then select this redefine crystal. And you can see this is the redefined crystal by expressing the new cell vector UVW as a linear combination of ABC. So in any direction you can increase the length. So for this structure, I would like to increase in the transport direction. So in this direct structure, C is our transport direction. Here you can enter 6. You can see I would like to increase 6 times in the C direction. You can take 5 times so that you can decrease the number of atoms and you can easily simulate during the session. So you can define 5 times in the C direction, select this preview, then you can select this build option. So 5 times you can increase in C direction, select the preview, select this build option. Now you can see the length of this nanoribbon, graphene nanoribbon has been increased 5 times in the transport direction. You can see this is the 3D viewer. You can select this ZX view. In this structure, you can see we have 40 atoms. 40 atom we have. You can see this is the total area of this lattice. Now we need to convert this structure into device so that we can define the left electrode, right electrode, and center region.
Excuse me, Deepak sir. How to select it? When I'm selecting, it's getting rotated. It is not selecting. Can you please help?
Like you want to select the atom. Hello, is
The way you were, yeah, sir. The way you were selecting, no, they were coming up as yellow. When I'm selecting, nothing is happening. It's
okay.
just
So you need
rotating
to
it.
select. You need to select this arrow first. You can select. You can draw the rectangle. You can select the atom.
Yeah. Now it's happening. Thank you so much, sir. Yeah, now it's happening. Thank you.
Okay. So now we need to convert this structure into device. So if you want to convert this structure into device, you can see this is the convert to device option. From this toolbar you can convert. Either you can select this build option, and here you can see we have the convert to device option. So this same option you can get from this build. Either you can take from this toolbar. So this is the convert to device. So based on your device structure, you need to define the electrode. Like we need to define the left electrode, right electrode, select this preview. Now you can see in this structure only 2 electrode is possible, left electrode and right electrode. So I have selected left electrode, right electrode, select this preview, then you will find the electrode information. Like this is our left electrode, right electrode, this is the center region. So once you select the electrode, left electrode and right electrode, select this preview, select this build option. So I hope everyone has been converted the graphene nanoribbon into device. So you can see this is our left electrode, this is our right electrode, this is our center region. So if you want to convert any structure into device, then you need to select this convert to device option. As per your device, you need to select the electrode, select this preview, then you can click on this build option so that you can get a device structure. So once you created the device structure, we need to simulate this device. So basically this is a 2-probe graphene nanoribbon device structure. So in this structure we have 2 probe. First one is left electrode and second one is right electrode. And the DFT parameter will apply in the left electrode, right electrode, and DFT plus NEGF will apply on the center part.
Excuse me, sir.
Yes.
How
ma'am.
are you going to decide the materials of the electrode? Because here both are having only GNR.
Yes, here we have the graphene nanoribbon electrode. So if you want to change the material from the left electrode and right electrode, you need to draw the rectangle, select the atoms, go to the replace atom. And from this periodic table, you can replace this carbon with any other element. So here I have created a device of the 2x2 graphene nanoribbon. So in this structure, both the electrode are same. Left electrode and right electrode are same. But if you want to change, so from this replace atom, you can. So the DFT theory will apply for the left electrode and right electrode, and DFT plus NEGF will apply for the center part. Now we need to simulate this device structure. So for simulating any device, any material, we need to select the simulator. You can see this is the simulator. And this NanoDCAL will help you to simulate the device structure. From this rescue, device option is not there. If you want to simulate the device, then this NanoDCAL will be very helpful. So this is the NanoDCAL, and we need to select this SCF calculation. So you can see this is the SCF calculation for the device. And whenever you select any material, then it will show the SCF calculation for the crystal. So this is our device structure, simulator, NanoDCAL, and you can see this is the SCF calculation for the device. So here you can include your parameter, electron temperature, cutoff energy, exchange correlation function, LDA, JGA, K-point sampling, contour integral, and this is the electrode. So this is the electrode parameter, like left electrode and right electrode. So we need to define the electron temperature, electrode voltage, K point for the left electrode, and electron temperature, electrode voltage, and K point for the right electrode. Any voltage you can define. Like here, I would like to define 0. minus 0.2 at the left electrode and 0.2 at the right electrode. So if you want to define different, so that you can enter the value. So here I have taken minus 0.2 at the left electrode and 0.2 at the right electrode. So this is our electrode parameter, iteration control parameter, density matrix, Hamiltonian matrix, total energy, basis set, and this is the spin type calculation. So you can take no spin, because once you define any Spintronics application, then your simulation time will increase. So I would like to select the default parameter that software already taken. So once you define the parameter, you need to click on this generate file, so that your input file of the left electrode, right electrode, and device will be generated. So you can see this is the scf.input file of the device. This is the left electrode scf.input file. This is the right electrode scf.input file. So in this case, both the electrode are same. So first, we need to define the run the scf.input file of the left electrode, then right electrode, then you can move on the scf.input file of the device. So you need to run. You can see this is the scf.input file of the device, left electrode. Then you need to run the scf.input file of the right electrode. Then you can run the scf.input file of the device. You can see I have run scf.input file of the left electrode, right electrode, and device. So it will take some time to simulate the structure. So once you run the scf.input file of the left electrode, right electrode, and device, then you can go to the analysis. So whatever the parameter you want to analysis for any device structure, you need to select simulator, NanoDCAL, so for analysis, you need to select simulator, NanoDCAL, select this analysis. You can see these are the device analysis parameter. So as per your need, you can select the analysis parameter. You can see this is the density of state. This is the scattering state. You can see we need to define the K space point and energy point. This is the transmission spectrum. You can see this is the transmission spectrum, and photocurrent will take more time to simulate the photocurrent output. So here I am selecting this IV curve because this photocurrent will take some time. But photocurrent you can also analysis. You need to define the parameter, polarization basis, polarization vector, linear polarization, left circular polarization, right circular polarization, elliptical polarization, and oblique elliptical polarization. So these are the various polarization vector that you can select. Then you can define the theta and phi. You can also define the photon energy range, minimum energy, maximum energy, and the delta E. You need to also define the K point sampling. And if you want to fall the light, you need to select edit irradiate atom. Only center part you will get. You need to select so that the light will be fall on the center part, and then select so that their atomic indices will be selected. So once the atomic indices will be selected, the light will fall on the center region. Then you can select this OK.
So how you selected atom indices?
You can draw the rectangle and select the atom.
Is that also we don't have to type anything in atom indices?
Yes, ma'am. Can you repeat?
Yeah, just I want to say that only selection will suffice for the input to atomic indices. We don't have to type anything there.
Yes, yes. No need to type anything. Just you can select and the light will fall once you
Okay.
select the atomic indices.
Okay. Thank you, sir.
Here you can see this is the IV curve. This is the charge. You can see this is the project, none, atom, and orbital. So this is the projection. You can see this is the electron density for the device. So these are the various density. This is the potential. You can see these are the various potential that you can select for your device. This is the conductance. You can see K point sampling and number of energy point you need to define. You can see this is the thermoelectric current. You can select K point sampling and temperature range. Here you can see this is the Seebeck coefficient. In the right hand side, you can see these are the Seebeck parameter, energy range, and temperature range that we need to enter. So once you select the parameter, You need to click on generate file. So you can select this generate file so that their input file will be generated. Now you can see the input file of the device has been generated. Like we have generated the density of state.input file, scattering state.input file, transmission.input file, IV curve.input file, photocurrent.input file, charge.input file, electron density.input file, potential input file, conductance input file, thermoelectric current, and Seebeck coefficient. So these all input file we also need to run. So you can run all the analysis input file, and once the input file completed, then you will get the output file. As I have already told you that the device simulation will take some time to simulate the structure. Here you can see the device input file is in the running condition. So you can see it has reached step first. And for the step first, it has taken 5 minutes, 1 second, through matrix, hybrid matrix, total energy, band energy, grid charge, and orbital charge. You can see 1 minute 20 seconds for the second step. So you can wait till the simulation complete. Once the simulation complete, you will get the output file. So you can see here the IV curve is not there to plot the. So for the IV curve, you need to go to the analysis part. But if you show in the new version of the device studio, you can see this is the new version of device studio. So that you can easily plot your IV curve. You can see this is the IV curve. So this device studio is under development. So we will let you know once it will be successful. So there is no need to go into the MATLAB. You can easily plot your IV curve through this device studio. But if you use this device studio, then the MAT file you can import into MATLAB so that you can plot the graph. Now the simulation is running. And also you can see in the new version, we have extra advantage, like this is the build option. This is the molecule 3D builder. And here you can see we have the biomolecule. So biological fragmentation is also there. So if someone want to work on biological application, so biological molecule is also possible from this newer version. You can see these are the different molecule, biomolecule. If you want to select any molecule, you can see this is the particular structure. Any structure you can select and you can click in this dashboard. So you can see this is the bio fragmentation, and also you can see this is the R group segment. So these are the various fragmentation for the R group that is not available in this device studio. You can see there is no option for the biomolecule as well as R group fragmentation. And also you can see this is the ring fragmentation. So if you want to create any structure, like you can see, if you want to create a simple benzene structure, you need to select and you can easily create the benzene. So no need to go into the molecule 2D builder and import the material. So you can easily create from this molecule 3D builder, from this ring segment. You can see this is the biphenyl. If you want to create a biphenyl structure, you can see this has been selected. So this is the biphenyl structure. And one more advantage in this new version, you can see, if you want to simulate any material with the help of NanoDCAL, you can see you can also calculate the atomic force and state tensor. So atomic force and state tensor you can also study. And this is for the material. And also if you want to simulate any device, you can see this AC conductance is there. So this is the DC conductance, and here you can see this is the AC conductance. So it will take some time. So if you have any questions, so in the meantime, you can ask. And if you want to show the publication
We
papers,
have created these files, generated these files, density of the state, scattering states. We need to run these all, no?
yes, you need to run.
That is taking time.
Yes. Here you can see SCF is running. So once it will finished, I will run this input file. So in the meantime, you can also run. But I have simulated this property earlier. So if you want to simulate, you can.
Excuse me, sir.
Yes, sir.
If we use the same software, which paper we have to cite in article?
Okay, 1 second. Sir, as you know, for publishing any paper, first you need to purchase, because
Yes.
this is the evaluation license that we have provided to you. But if you want to publish any paper, then first you need to purchase. And if I open some publication paper, You can see this is the NanoDCAL software publication. You can see this is the electronic transport property of the two-dimensional tetragonal zinc. You can see we have simulated the photocurrent.
How much the charges for NanoDCAL for 1 year for single user?
So if you go for the single license for 1 year, then the price will be 1.4 lakh plus GST of the
Okay,
NanoDCAL
and
software.
after finishing 1 year, we can use that one.
Yes, yes.
Okay. 1.5.
And also we have the 1 year license, 3 year license, 5 year license, and perpetual license also we have. And for the single license, as well as multiple license, like 5 license, 10 license, 20 license. So this policy also we have.
For 1 year license, we need upgrade or no need?
So sir, it depends upon you. If you want to take, then there is some, but 1 year free technical support we can provide. 1 year free technical support and update.
Okay.
But you want to take after 1 year, then some charge will be applicable.
Okay. Thank you.
So you can see these are some publication papers. So also you can calculate electronics property, optoelectronics property, and thermoelectric application.
But for electrocatalysis,
Yes, electrocatalysis you can also study.
is there any paper? Please let me know.
Yes. Wait, sir.
Electrocatalysis and supercapacitor battery.
You can see this is the publication papers for the supercapacitor battery application using the first principle non-equivalent green function method by using this NanoDCAL software.
Thank you.
And also thin film device structure you can also study. So you can open the Google Scholar and just you can type your particular device or in particular material, and you can also enter plus NanoDCAL. Then you will get the publication paper related to the NanoDCAL software. And same for the rescue. You can search you can see this is the rescue. I will also share some publication papers. So you can see NanoDCAL and rescue publication paper. You can see this is the biosensing application. So this is the formaldehyde gas sensing property of the transition metal dope graphene first principle study. Like also we have you can see this is the biosensing application. And you can see the same structure I have created. And you can see this publication paper is published by the NanoDCAL software.
For energy calculation, we have to only copy paste that program, Professor, sir.
Yes, sir. Yes, sir.
Just copy.
You can copy the program command that I have given. This command. And also you can include this one. So this is the complete command. So you can copy and paste in the input file.
Okay, sir. Okay. Oh, you said
So I have installed this origin. So But I never use this origin software, so I will take some time. Oh, origin.
It is similar to the Excel, sir. Same.
Yes, sir.
Origin is similar to the Excel one for plotting the graph.
Okay, but I will take some time.
Okay, okay.
So for any theory and any background equation, visit our this nanoacademy.com, and then you can go to the document and tutorial. So you can see these are our product, NanoDCAL, so that you can simulate any material, any device based on the DFT and the NEGF method. So this is the advanced version of this NanoDCAL that is written in Python and Fortran. So this is the rescue that is dedicated for the material simulation based on the density function theory and density function perturbation theory. So this is the NanoDCAL, and rescue is written in MATLAB and C. NanoDCAL plus and rescue plus is written in Python and Fortran. Also, we have this QTCAD software for the quantum technology spin qubit devices in semiconductor. Like if we talk about this QTCAD, you can see. So this QTCAD is a finite element based simulation platform for the quantum technology that is developed by this Nano Academy technology. So if someone want to work on quantum technology, then this QTCAD will be very helpful. So in this QTCAD, we have the electrostatic tools that will solve the confining potential of the quantum dot in the semiconductor nanostructure, so that you can find the corresponding envelope function of the electrons and holes. Also, we have the valley splitting tools for the valley nanostructure. We have the exact diagonalization tool for the rigorous treatment of the Coulomb interaction between the few electron system. Also, we have the master equation solver for the quantum transport calculation in the sequential tunneling regime. So that enable to treatment of the Coulomb blockade and the calculation of the charge stability diagram you can get. And this QTCAD comes with the Python interface. So you can see I have installed this QTCAD version also. So you can see this is the visual code that is basically a interface of the Python. You can see. This is my QTCAD. Here you can see in QTCAD we have three simulators. First one is the device simulator, we have the transport simulator, and we have the qubit simulator. In the example folder you can see I have written some commands. You can see this is the adaptive meshing, this is the adaptive Schrodinger equation, this is the background charts. So if I run some examples, you can see this is the gate all around field effect transistor. If you talk about the You can see these are the features. And this is the workflow. So if we talk about the QT-CAD workflow, so typically the user will first select the spin qubit technology, which could be based on the different type of semiconductor devices like thin film, FinFET. So once the technology is selected, we need to generate the 3D representation of the structure. That will be possible from the GMS. And basically the GMS is a open source third-party tools that will help you to generate the GMS file. And once you generate the GMS file, that GMS file you can import into Python API through the QT-CAD. You can also define some material parameter. You can see I have already written. And once you simulate this structure, you can visualize the result from the visualizer like PyPlot, PyVista, and ParaView. So this is the workflow. You can see through this Python API, you can write the command in the QT-CAD. You can see I have enabled the QT-CAD in this Python interface. You can see we have defined some constant value like physical constant. I have imported the mesh file that I have created from the GMS. You can see this is my GMS. You can see this is my GMS. So the 3D representation you can generate from this GMS application. And this GMS is a open source third-party tool. Like you can see, if I would like to open some file, you can see this is the Graphene. So you can see this is the gate all around field effect transistor. We have the source, drain, and this is the gate. So this is the gate all around field effect transistor. So basically this is the TCAD software based on the FEM method, so that you can study the spin qubit devices in the semiconductor. So for any product, as per your need, you can select the product, and then you will find the theory and tutorials. You can see these are the tutorials. Like this is for the molecular electronics.
Sir, excuse me, sir. It is possible to show the GUI for WASP?
So you can see one second.
Just show me.
You can also get the GUI. You can see this is for the WASP, LAMS, Obito, Quantum Espresso, and Gaussian. So in that license, we did not enable the license for this WASP, Obito, LAMS, Quantum Espresso, Gaussian. But whenever the user will purchase, then all these options will be enabled.
If I
So
buy the interface for 1 year, we can get all the
yes,
this interface or only one?
no, sir. Every simulator you can get.
Thank you, thank you.
So our interface also support with the WASP, Gaussian, LAMS, Quantum Espresso, and their input file you can generate. Now you can see the scf.input file is simulating, so it will take time. So if anyone has any query, so you can ask. So I will try to help you. And for any future requirement, any technical support, so you can let us know so that we are ready to help you. So this is my contact details. So either you can drop the mail, either you can contact through this number. So from my side, thank you so much to all of you for your registration on this 2 days hands-on training on NanoDCAL and RESI software. So after this hands-on, we will provide you the license, recording video, and also we will provide you the certificate. And for any technical support, you can let us know. And also for the videos, you can visit our YouTube channel. This is Impulse Technology.
Deepak sir, thank you
Yes,
for
ma'am.
this informative sessions. Just I wanted to know in your this job description, no, job manager, I can see that the simulations that you ran for the device has been completed
Ma'am,
for many.
yes. I have opened another project. Previously, I have opened
Okay,
another project. So that's why
okay,
here you can see the input file
yeah,
has been completed. But here you can see this file in the background, the file is running.
okay. Because for me, even the first one is not completed.
Yes. So for the videos, you can visit this website, this YouTube channel. You can select this playlist, select your product. Like you can see, this is the NanoDCAL software videos.
And Deepak sir, yesterday you said that you would find out the software or the means the command that would be used for calculating adsorption energy. So, do you have any information on this? No.
And absorption energy you can calculate from our another software, which is
Yeah.
SetForce.
Set force, but that was about the absorption energy, not adsorption. AD adsorption, because I'm working on nano catalyst, and when we talk about the catalyst, it has to absorb the molecules. So it doesn't absorb it; it adsorbs. I mean, they are like pinging on the atom itself.
Okay, ma'am, no issue. I will check and I will let you know.
Yeah, you have my number. If you can again some insights, just share it with me, right?
Yes, ma'am. Yes, ma'am. I have your number.
Yeah, thank you so much, sir.
Okay, ma'am. Thank you so much. So once again, thank you so much to all of you.
Thank you, sir.